So in this topic we will see minimum spanning tree. So first of all we should know what is this spanning means. Spanning means something to cover entire. So suppose I am telling you we have a graph with node A here, node B, node C and node D, okay, and we have these many edges. Suppose we have another node and edges, okay. So in this graph, if you notice, we have 5 nodes and we have 1, 2, 3, 4, 5, 6, 7. Total 7 edges are there. So when we say spanning tree, the word comes tree. So what do we mean by tree? So basically we have a property of tree. If we have n nodes, if we have, let it call as a vertices in terms of graph, if we have v vertices, then the tree must contain v minus 1 edges. So what do you mean by this? Suppose we have 3 nodes, you are asked to form a tree. So you may have this tree or you may have this tree or you may have this tree. So if you notice, in this tree we have only 2 edges. In this also we have only 2 edges. So for 3 node we have only 2 edges. What if we exceed this number of edges? So if we exceed this number of edges, let's say by 1, so we are saying the total number of edges could be 3 in this tree. Oops, this is not possible because this form a cycle, and we know that tree is an abstract data type whose all vertices are connected and there is no cycle in it. So here we will not include this. So this property holds for every tree, whether it is binary tree or n-ary tree, tertiary tree, whatever. So in this graph we have total how many nodes? We have 5 nodes. So we must have 4 edges when we form tree out of this graph. So what is the criteria to select edges? What is the criteria? So we don't have any criteria right now. We may have some weight here, we may have some distance. So we must have some weighted edge. In this connected graph, we must have some weight on these edges. Now the word spanning tree means all the vertices should connected. So if there, suppose we have a connected component here and we have a connected component here, we have 2 connected component. So the spanning tree for this connected component will be 1. There will be 1 tree here and 1 tree here. So this will form spanning forest here, not a spanning tree for each of this component. So what is the criteria? So for that, let us assume we have some weight here. This is 1, this is 1, this is 2. Let's say this is also 2, this is 3, this is 4 and this is 5. Fine. Now what? These 2 algorithm uses greedy approach. So for those who don't know about greedy approach, you can go back and see my greedy approach algorithm video. So basically I'll brief it. Greedy approach is one of the algorithmic solving problem approach, like like we have dynamic programming problem, we have branch and bound, we have divide and conquer, and so on. So in greedy approach we choose wisely our subject. So what is the subject here? Subject is to choose edges for a spanning tree with minimum cost. So I have to select the edges in such a fashion that the total cost of this graph would be the minimum. So what would you do if you are a if you want to do some greedy approach? What you will do? You will start picking up the edges with minimum cost. So let's pick up this one. We have AE, which is of weight 1, then AD 1. Remember, we will not include that edge in our tree, which will form a cycle. Okay. Thereafter, we have this 2 or this 2. Okay. So let's include this one. Then this 2. Then we have this one 3. If we join B and A, this will form a cycle. So we will not include this. So this is not included. Then 4. If we join C and D, it will again form the cycle. So we will also not include this. If we include this E and C, which is of 5, E and C, this will also form a cycle. So we will not include this one also. And if you remember what I told you, we have 5 nodes. We require only 4, exactly 4 edges, which we have already covered. So you may check further, but it is not required. If you have achieved this 4 edges, it will definitely form a tree which will include all of those vertices. Now what? How to implement, how to solve this problem using our algorithm. So let us understand first this algorithm. So this is minimum spanning tree Kruskal. In this, we take a set A, which is initially empty. For each of this vertex in this graph, we do make set. If you haven't watched my video of union by disjoint set data structure, you go back and watch that first, because you will have some understanding of disjoint set data structure. And there is another video which is efficient union find algorithm, which will explain you how we achieve disjoint set data using disjoint set data structure, that union find algorithm in an efficient manner. How? By path compression and union by rank. So the improvement part is in this union. So we do make set. So what we do make set? In this make set, we pick up each of these vertices and treat them as a one set. So this is one set A, this is E another set, this is B another set, C another set, and D another set. Then second is sort the edges of E. In this graph we have many edges. We will sort them in non-decreasing order of their corresponding weight. So we have different weights here. So we will sort them by their non-decreasing order of their weight. So first we have AE here. So we will write here AE, then AD, AC, BC, then we have AB, then we have CD, then we have EC. Now first we will pick this edge AE. So in this AE, A is U and E is V. So if you see, for each edge UV, find set of U and find set of V and then compare it. If it not match, it means both these are in not the same set. Then you include this edge in the set A, which is what? The tree edges of a spanning tree. And if it is the same, it means both these nodes are in the same set. It means this two vertices is already included as an edge in this set A. Then you don't include it. and then you come out. When you are including this edge UV in A, after the doing that, you have to merge them also, which is what? Union. So first A and E. What is the super parent of A here? Is A itself. What is the super parent of E here? Is E itself. So these two are not equal, so we will merge them in one set, and we will include this edge AE in set A. In set A. Again, we will pick this AD edge, check for A. What is the super parent of A? What is the parent of A? Is itself this set and this A. What is the super parent of D? Is this one. These two are not equal, so we will merge them and also include this AD in our set. Fine. Again we have AC. Super parent is this one. C is here. Include here and include here also. AC. Next is BC. What is the super parent of B here? Is B itself. What is the super parent of C here? C here is this one. So these two will be merged and this will be included, BC. Again, if you check for AB, we have A, which is this set, and B, which is the same set. So super parent for A is A, B is also A, since these are linked up. So AB is no more included here and no more disjoint set is formed. So we'll come out of the loop and then we return this set A. So this set includes 4 edges, and as I said, there are 5 vertices. So total number of edges will be 4 exactly, and so this is the minimum spanning tree. So which all included? This one is erased, this one is not included, this one is not included. So 1, 2, 3 and 4 edges included. Now let's see what is the time complexity of this algorithm. So we have, for each of the vertex we are making set, which is nothing but O of V. Sort the edges in non-decreasing order. At best we can achieve O of E log E. Then for each of this edge, this edge, we have to perform union. We have to check for find set, which is O of 1. Finding set is O of 1 since it is in the linked list, and we have to find this union. If you refer this Corman book, there you will find that union operation is sum of order of V, which is non-growing function, means it is not much growing function, which is almost equal to O of E log V. So if you sum up, this is O of V plus O of E log E plus O of E log V. Now since we have a upper bound, so we can include which we can write, this is 2E log V plus E log V, which is nothing but E log V. So the time complexity of this minimum spanning tree by Kruskal method is E log V. So we can improve upon this by performing Prim's algo.